Okay, so we are going to look at advanced Lewis structures, and why they're called advanced is we're really sort of going to break the rules that we learned last year. But when we reviewed grade 11 as a whole, then we only reviewed covalent structures with the bubbles and the lines because ionic is too rigid, plus, minus, plus, minus, plus, minus. So we're only going to do covalent. Okay, so nonmetals. So when you look at the periodic table, nonmetals are really the ones to the right of the staircase. That's not that many choices. Okay, so you're going to see the same atoms in the questions over and over and over. Okay, which is good. So hopefully you'll start to see a little bit of patterning here. When you go to do the homework, this first question, 227, number 5, all of these follow the rules. So if you would like a little bit more practice like what we did in grade 11, that's what these are, and then it starts to break the rules, okay? So don't just do these and be like, oh, I'm good. No. These ones have the expanded octet ones, and we're going to draw Lewis structures for polyatomic ions. Some of them, I've asked you to skip letters because there are polyatomic ions that have 3 atoms. We're just going to focus on 2, like carbonate, C and O, nitrate, N and O, those ones, okay? But this can be expanded even further, which you can do next year, okay? So it is just like the structure of the atom. We cannot see a bond, okay? So this is still very theoretical, and if you happen to watch that 100 Greatest Discoveries in Chemistry, they show Kekulé, and literally we draw dashes between atoms because that's what he did. So it seems so simple that he used that notation, but that's really all it took. So once Dalton started to describe what was happening, that elements came together, that matter wasn't just random, he called it combining capacity instead of ionic charge, those kinds of ideas, then they really started to consider not just atoms, but what was a compound, okay? So Franklin stated each element, they called it bonding capacity. Kekulé drew the lines, they drew the bonds as a dash. And then Van Hoft and Lebel, 3D structures. This is what we're going to do tomorrow. And those of you that would have taken 12U Bio would have talked about VSEPR and the 3D shapes. I feel like Mr. Adams calls it VSEPR, but that touches my dark side, so we're going to call it VSEPR. And then the idea about, well, we would like to predict and the trends, and Mendeleev being able to sort the elements. So the big idea was that they thought because this column, the noble gases, because they don't naturally react, then they were considered stable. That makes sense. And then the idea was that every element wants to lose or gain or share electrons to become like the noble gases. And that's true sometimes, but sharing can get out of control and weird things can happen, okay? So, and in fact, when I was in high school, we called these inert gases because it was like law, no, never react. And now we know, well, there's always exceptions, right? We can force them to react under very stringent conditions, weird things can happen. So we had to change the name, okay? But these guys you probably have never heard of. Of course, Lewis is a person, Gilbert Lewis, and in 1916, he sort of made it succinct and usable, okay? So atoms, he definitely stuck to the idea that atoms or ions, want to be like a noble gas. He used words like stable octet to imply 8 electrons in the outer shell. Electrons are most stable when they're paired. We still think of it that way as well. And bonds form, so atoms achieve the stable octet. And one of the big problems with this is sometimes, like hydrogen, for example, doesn't even have 8 electrons to begin with, or even close to 8, it only has 1. Is it going to gain 7 to get to 8? So sometimes this sort of notation doesn't make sense, okay? But this we still consider to be true. Metal atoms are going to lose electrons, non-metals gain. You guys know that. Metal atoms become cations, non-metal atoms become anions. You can also share, and sharing occurs between non-metals. So that is still true. It just can't be to always get the octet, okay? That doesn't make sense. This idea as well that we're not going to leave electrons unpaired, that's weird, okay? That's very unstable. In fact, they think that elements that can do that, like oxygen, if you've heard the word free radical, or like antioxidant, trying to get rid of unpaired electrons in oxygen, they think that's why we age. Okay, so very, very, very unstable, which is not what atoms and compounds want. Okay, so we're going to focus this year on the exceptions. So the octet rule really only applies to the carbon atom and beyond. And in fact, we haven't really talked much about carbon. How does carbon behave in a bond? Because, you know, sometimes your teachers will say things like plus or minus 4, and carbon actually just shares. So we're going to do organic chemistry last. That is an entire unit on the chemistry of carbon, okay? And then once we get past the second period, then exceptions are frequent. So if you look at your periodic table, elements like chlorine, phosphorus, they have more than one charge written underneath them. And we don't really consider that in grade 11, right? So we're going to look at how those elements can break the rules and not do the count the column thing, okay? So Sidgwick is a scientist who said, okay, well, Lewis, you're sort of right. It is desirable, the octet, but not required. So we're going to look at how one atom can contribute both electrons that are shared, how one atom can steal electrons, steal a pair of electrons, if it's very electron greedy, that kind of thing, or high electronegativity. And the big one is, how do polyatomics, why is NO3 have a charge of -1? So what is going on, okay? So the big thing is, we are going to break the rules. So if you are given a polyatomic ion, so I will give you the structure or the compound, the formula, and the charge. As soon as you see that polyatomic ion, you're not going to do what we have done before, okay? So what I'm going to do, I will write out the steps that I'm doing, and on the right-hand side, I'll draw the picture. Again, because you're going to see that there are patterns. So we're going to do NO3 -1. This is going to be very similar to other polyatomic ions that look like this. So you don't have to do all the steps that I'm doing, like you don't have to show all your work like I am, because you might notice, you'll be like, oh, I don't need to, I know what this is supposed to look like. So it's up to you. But I do recommend, whether you have the note printed off or not, that you write it down now as I do, okay? So that you can see what I did. So as soon as you see a polyatomic ion, you are not going to do bubbles. You are not going to do what we did before, okay? I guess this is really the only thing that is going to be very similar, finding the number of valence electrons. But how we arrange them is not, we're not going to draw, like, we're not going to do stuff like this to see how many bonds nitrogen needs. We are not going to do that, okay? Polyatomic ions, it makes no sense. Why are there 3 oxygens? Why is there only 1 nitrogen? Why does it have a -1 charge? So we need a different way to deal with this. So the first vital step, so in fact, write it down and then put a highlight around the step. You're going to count the number of valence electrons we have to put in our structure, okay? So again, you can certainly streamline this process, but I'll show what I'm doing, okay? So we have 1 nitrogen, we have 3 oxygens, I'm going to put oxy so it doesn't look like 30. And we have a -1 charge. There's only 1 polyatomic ion that's positive, NH4 plus. All the rest of them are negative. Is there anyone who doesn't know where I got 1 nitrogen, 3 oxygen, and the charge from? That's important, okay? And this would be given to you, okay? Even though it is on the back of your periodic table. So if it happened to say the carbonate ion, that's on here, I will give it to you, okay? All right, so how many valence electrons does nitrogen have? 1, 2, 3, 4, 5. Fifth column has 5. And remember, we're dealing with only nonmetals, so you can kind of direct your eyes over here if you like. Then oxygen has 6. 1, 2, 3, 4, 5, 6. But we have 3 of them, so we have to multiply. And then we have a charge of -1, so I'm going to add in that negativeness as well, okay? So 5 plus 18 plus -1. Ooh. That's going to mess us up. Just add in 1. These are, or make all of these negative, okay? Either way. So make them all the same, okay? Because you want to get an even number. So 3 times 6 is 18, plus 5 is 23, plus 1 is 24. Or you can do it this way, -18 and -5 is -23, and -1 is -24. You can do it that way too. Why can you do negatives? Electrons are negative. And then the math works out. Yes. Whatever makes sense in your brain, to be honest. Because technically, you don't have to show it like this either. And what you might find is you'll do a bunch of these and you'll be like, it's very similar. You might think it's very similar. I don't need to show all the work she does, which is fine too. okay, so sometimes students are like, Ms. Todd, make a good guess. Or what? There's really going to be two choices, three choices. It'll either be two elements on the outside and then it's a line. It'll be three elements like this and it's sort of like a peace sign. Or it'll be four and then you just do like a compass rose. Yes. 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 So let's say we did CO3, 2 negative, then you would do carbon plus oxygen plus 2 or minus, minus, minus. Whatever makes more sense in your brain. Because the sign doesn't really matter because what we're going to do is just use the 24 to show how many to put. That's all you really need, to be honest. Okay, so I'm just going to show how these elements are arranged. Now, these technically are not, H2O and H2S are not polyatomic ions, but I just snuck that in there so you just remember, but it's sort of logical, like you can't make hydrogen the central atom, but this is the only exception, even when we do VSEPR, okay? So the central atom will always be, or the atom in the middle will always be the first one, okay? So we have nitrogen in the middle because it's written first. And then because there are three, I'm going to make it a peace sign. Okay, so one in the top, one over here, and one over here. And that's not random. I mean, it seems random, but you can actually measure the bond angles the farther you go next year with this. So the fact that they don't do this is real, okay? They can do X-ray crystallography and measure the bond angles. Now, if you drew it like this, I probably wouldn't take marks off, but really start to think about symmetry and repulsion. These oxygens do not want to be close to each other if they don't have to be, okay? So just do your best. But definitely the first element in the formula will be the central, okay? So we have our 24 electrons. I'm going to highlight that too. This is what we are going to place. I should have squished more, but that's okay. You guys have another box, right? Okay. Okay, so I have to go on, but you guys can just fill in the blank space if you want. Everybody good? Okay. Because these step 2 and 3, you might eventually just want to do together, to be honest. So the first thing we have to do is make a bond. Terrible one. Okay? So you want to make a bond. At least one. Remembering always, how many do we need? 24. And we are not following any rules. Yes. 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 But sometimes we might have to change to double bonds, so it's up to you. Yes, you can. Okay, so even though nitrogen, it has 2, 4, 6, normally we want to get to 8, so that might be a trigger in your brain. This doesn't make sense, Miss Todd. Yeah, you're right. But we're just going to leave it for a second, and we're going to fill the octet of the surrounding atoms. Okay, so we're going to fill in the octet for the surrounding atom, okay? So I'm going to do it, I'm going to redraw a new one. So again, when you do this later, you're probably just going to keep going. You're not going to redraw it every single time. Now, you certainly can, but you might find that you don't do that, okay? Okay, and don't push your out of your brain things you already know. What does oct mean? You know that that means 8, okay? So don't forget what you know. 2, 4, 6, 8 around oxygen. 2, 4, 6, 8 around oxygen. 2, 4, 6, 8 around oxygen. I know that nitrogen does not have an octet. I'm not worried about it right now, okay? No. But there's you can go there's 2 spots. Down like the big one. Okay. Do you want some paper? Okay, so we have to check what we've placed so far. In the back of our head, what are we always thinking about? How many? 24. Yes. So I underline total, so you're looking at the total number. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. If you drew lines, just remember that the lines count as 2, okay? So we have placed 24 electrons. Is that our total from the beginning? Yes. So what that means is we cannot put any more on here. So that's why that's step number 1. We highlighted it. That's why it's so important. That's going to guide how many electrons go in your diagram, okay? Okay, do we have an octet? No. So there are two options, okay? So I'm going to write the first option, I'm going to write which applies here, and then I'll make up some random example for the other type, okay? Because it's actually a little bit easier. So we cannot place any more electrons. We can't just go put 2 dots by nitrogen, which is tempting because that's easiest. We can't do that because we've already accounted for the 24. So every step you're thinking in the back of your head, no more than 24, no more than 24, no more than 24. And that's why this step is so important, okay? That's why we highlighted it. Okay, so all the valence electrons are accounted for like we have, but we do not have an octet around the central atom. So what can we do? Well, we talked about in grade 11, you can have single bonds like we have so far. With covalent compounds, you can have double and you can have triple, right? So we can move a pair of electrons and make a double bond without adding more electrons. All of these oxygens, would you say they look the same? There's nothing different about them. They all have the same number of electrons. So it doesn't matter which one you pick. And again, those of you that took 12U biology might have talked about resonance structures, that you can have different forms of the same thing. Most people, I think your textbook starts with the right-hand one. I think of it like the top one. It does not matter. So what we're going to do is we're going to take one of the pairs. So I'm going to move this one. And then I'm going to move it to make a double bond. Okay? Now, this may be a really a nasty sketch that you don't want to draw eventually, okay? So down here, same. So you might see this notation like this: dot, 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 oxygen, dot, 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 dot. So this is trying to show a multiple bond. So this picture here is a little bit nasty. Yes, it's a little bit cluttered. So when you do these questions on your own, you might not want to draw this. You're going to skip right to the final one once you get here. But I'm just going to draw this in here, okay? If you have nitrogen and something simpler like carbon or hydrogen, you might make a triple bond, but that's very rare. Normally it will be double, okay? And normally it's when you have an oxygen. I just realized there were oxygen instead of surrounding atom. Usually, if you remember, most of the polyatomic ions have oxygen. Okay, option 2 does not apply to this, but it's actually a little bit easier. So I'm just going to sketch a random one. So let's say you got here, which I realize I'm trying to keep it as simple as possible. And let's say our total was 8. How many do we have right now? 6. So then you would just be like, okay, another dot, done. Okay? So it's really when you've accounted for them all that you might have to move them. So always thinking in the back of your head about how many total, that's going to be the most important. And again, you can put that anywhere if you prefer it. Down here, over here, doesn't matter. Put them in. Yes. Let's say, okay, so you place 6, but let's say our total was 8. So we haven't reached the total yet. Not like this one. We had placed 24. Our total is 24, so we can't put any more. This one would be we placed 6, but our total is 8, so we need more. Okay? Yeah, you're just putting them in the right spot. Okay, so when you do this, showing the movement, you don't have to do all of that, okay? You can do this, maybe fill in the central, and then most people will want to just skip to the end, but that's fine. So now we have arranged where the electrons are going to go, but this is cluttered and nasty. We're going to make it look a little bit better, okay? Yeah. Yes. Okay, we good? Can I go? Okay, so last. Thank you. Okay, so I'm going to draw lines to represent the bonds. So we had 2 pairs, 1 pair. Oops. You can double check one last time that you've got 24 if you want. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. If you are so inclined and you want to know where the -1 comes from, so oxygen, what's oxygen's charge usually? How many bonds does it want to make even? What's oxygen's charge? As an ion. -2, -2. So this one with the 2 bonds, that makes sense, okay? So I'm going to call this, like this is normal. It's not an issue. This one has only 1 bond and extra negativeness. So let's call this -1. So then you would think the charge is -2, but how many bonds does oxygen usually want to make, or what's its charge? One, +1, +2, +3, -3, right? So normally it would only have 3 bonds. How many does it have? 1, 2, 3, 4. So it's missing its pair. So let's say it's like +1. So -1 and -1 is -2, +1 is -1. So that's where the charge comes from. That is not a requirement. You do not need to do that, but if you're curious. And again, when you go to do this, there is plenty of steps in the middle you don't have to show, but I highly, highly, highly recommend you do that counting first. You don't think about don't try to draw bubbles, none of the old rules, okay? For polyatomic ions, they do not follow the rules except for counting the electrons, like how many, the columns or whatever. That's about it. Okay? So the next two, these are not polyatomic ions. There's no charge. Or so for these ones, if you want to do the old way with the bubbles and stuff, you can do that, okay? So SF2 is just like we would have done last year. Now, for this type of question, so for example, this one is going to break the rules. We call it an expanded octet. And I can't ask you to figure out what that is. I have to tell you. So like last year, where we followed the rules, I might have said to you, draw the Lewis structure for sulfur and fluorine. I didn't tell you the formula. This time I will, okay? And even when we do 3D shapes. So follow what I've said, okay? So how many valence electrons does sulfur have? What column is it in? Yes, good. How many does fluorine have? The next one at a 7, okay? So this one, sulfur's the middle, just like or central. Actually, I won't cheat. Oops. 1, 2, 3, 4, 1, 2. Yes? And you decide, are you a bubbler? Are you a line person? Whatever you did last year is fine. Okay? Both of those are perfectly acceptable. You can do whatever you did last year. That's totally fine. But then you go over here, you're like, Ms. Todd, we just drew SF2. Why is it SF4? Okay? So this is what we call an expanded octet. Yes. Well, sure. But you're going to see tomorrow that the outer atom is less important. So, chemists are lazy, so then we don't write them in. But in grade 11, I made you, so. Good question. Yes. It doesn't matter. I just did never eat shredded wheat and then went back and paired them up, so. And actually, technically, this should be angular with these at the top and the F's at the bottom, but we can leave it like that for now. Okay, so again, when you have an expanded octet, that is not going to be predictable. You cannot predict it, so check what I have written down, okay? And don't automatically assume, oh, Ms. Todd wrote it down wrong. No, because now we are going to break the rules, okay? This one, when you do ones that are weird, that don't follow the crisscross rule, then you might want to do bubbles at first. It might make more sense, but it's up to you. Okay? So I'm just going to, if you want to draw it the other way, I just kept going like clockwise. It doesn't matter. Okay? So, and like I just said to Heather, I'm not going to draw these dots in around the fluorine because the surrounding atom is not as important. And I don't want my picture to be cluttered. If you want to leave them in there, you can. 100% in grade 11, I definitely made you. But I just don't want this example to be cluttered, okay? So fluorine needs to make one bond. That's what you're used to, right? So fluorine is a very electronegative atom. In fact, it is the most electronegative, which means it's very, very, very greedy for electrons. So what fluorine can do, it can actually steal and break apart a pair, okay? So the one idea we talked about on the one of the first slides, you should not leave electrons unpaired. So we paired up what we could, and then we're going to follow the formula you're given. So it says SF4. So pick one of the pairs, doesn't matter which one, and the fluorine can break apart the one that's already paired up. So should I leave it like this? Is SF3 a possibility? Not that I won't give you the formula, but no, because this one is by itself. It would not do that, okay? This is like super nasty, destroy cells. No, we're not doing that. Okay, so it has to be paired up. Okay? Could you make SF6? Yes. That's not what this is, but you could. Could you make SF5? No. And SF6 would be the max. So there is a limit to the expanded octet, okay? So what do you look for when you're asked to draw a Lewis structure? Is there a charge? Like, is it a polyatomic ion? I forget if the questions say, like, do the polyatomic ions, but it gives you the charge, so look for the charge. And then if there's a charge, do it the other way. And then if it's a weird formula, then bubbles might be helpful, okay? If you don't like bubbles, then you can redraw this when you're done. That's fine too, or you can leave it like that. You can draw in the dots around F, but again, they're not as important, so if you're not a cluttered kind of person, then maybe you want to leave them off, okay? So remember, these questions are not all created equal, okay? These 227, definitely, I think it's 227. One of the pages, 227 or 229, definitely it's old school Lewis structures that follow rules. So please don't just stop there and then don't do anything else. Give the polyatomic ion ones a try. There is about 20